Hello, everyone. There's still quite a few spaces here available at front, so feel free to come forward because the hall is very, very long. Without further ado, we've got Sven Arends here on the stage, senior ML engineer at Picnic. And in his free time, he likes to work on embedded devices, for instance, having his plants watered while he's on holiday. But I'd like to know how, they count groceries with computer vision at Picnic. So give it up for Sven.
Nice. Can I get my slides as well? Perfect. Well, thanks for coming to my talk about how we automatically track our inventory, which in our case is groceries, and how we do that with computer vision. So my name is Sven Arends. I've been an ML engineer at Picnic for the last 4 years. Worked on almost all of our models, ranging from regular forecasting to time series forecasting to, well, now computer vision. I like to engage in my free time in open source projects, work on embedded devices, and after a long day of hiking, I love to go to the sauna. Enough about me. Picnic is all about making grocery shopping simple, fun, and affordable for everyone. And we do that by virtualizing the supermarket into your pocket by having an app. But while we have a very virtual supermarket, we have a very physical supply chain. So where in a normal supermarket, people go every time they want to get groceries, they get into their cars, go into the supermarket, pick their groceries, and drive back. We actually have suppliers deliver the groceries directly to our fulfillment center, from which we drive with our electric vehicles with an optimal route straight to your house. And what I think is very cool about Picnic is that we run on a lot of in-house built technology. Obviously the app, as you might be familiar with, but actually most of the technology is built in-house and is inside. From controlling our control software in the fulfillment centers, to our planning optimization algorithms, to building also apps for the runners. So the runners are our delivery person that deliver the grocery to your homes. And actually we have created our own apps on those devices that precisely tell them which totes to scan, where the address is. We have our own Picnic navigation, which takes into account the specific traits of our vehicle, which I think is super cool. And speaking of that vehicle, that's also something that has been specifically designed for Picnic. And we have quite a few other hardware products designed specifically for Picnic. And what is very cool about this is because we own this whole vertical stack, we get a lot of visibility and a lot of data. We have a large and mature data team that structurizes this data and puts it all into our data warehouse, which then opens up a lot of possibilities for machine learning, ranging from recommendations to time series forecasting. On the store side, for instance, we do search result ranking. We do product recommendations. So we want to, of course, that you are able to find every desire that you have in terms of groceries at Picnic, but maybe you're not familiar with completely our assortment, and then we'll try to show you products that you might be interested in. We do payment fraud detection also in-house, where in the Netherlands, with Ideal, you prepay your groceries. In other countries that we're active, for instance, in Germany and France, often afterpay is more standard, but with afterpay means that it's not per se guaranteed for us. And we, of course, want to detect a small percentage of fraudsters as well. On the supply chain side, we have, for instance, article demand forecasting. So we want to specifically know how many bananas will we sell tomorrow, next week, in 2 weeks, and in a couple of weeks from now, on an exact day, and also an exact region and an exact day part. So even if we're going to sell it in the morning and in the afternoon. We do stop time estimations ourselves, so we would like to know how long will we stop at the customer, because you can imagine if we deliver the same grocery basket to a house or to a large apartment building 6 stories high, no elevator, that is quite a big difference in stop time. We do people planning because we are very flexible with our demand, so we need to be flexible with planning as well. But of course, as a person, you want to know a couple of days ahead when your shift is due. And then on the customer success, we do message classification. We get, luckily, a lot of compliments when we deliver the groceries, and those positive compliments we want to forward to the people in operations as well. And the ones that aren't so favorable, we would like to tackle and see where we can improve. And we also classify the skill required to solve a problem. So if there's clearly something missing in your delivery, we can maybe solve it by any customer success agent. But if it's a more difficult problem, then actually some customer success agents might be more suitable. And we have lots more of these products that we built in-house. But I think what is also very cool is that as an ML engineer at Picnic, we call ourselves full stack in the sense that we are there when we scope it from a business problem to all the way productionizing it and monitoring it. And scoping really means that we also challenge if we even solve this, if we even should solve this with machine learning. Because often we can solve with a few business rules actually 80% of the problem. And then using ML is just way overkill, and we can spend our time more wisely somewhere else. We analyze the problem together with the business analyst. And of course, then we do lots of experimentations. Recently, we now also use Marimo notebooks, which actually Vincent will give a talk on tomorrow here at PyData, which I think is a very handy tool for this. And then we productionize it. And when we productionize it, we have basically two flavors. We either do batch jobs, cron jobs, or based on events. And we have services, because in some cases, like the payment fraud, or maybe when you have a question, we immediately want to give an answer. And in those cases, we build web services using Fast API. And we foster a culture of you build it, you own it, which means we value high quality code with type-ins, docstrings, tests, and of course monitoring tooling. But hopefully that won't be too often necessary. But let's dive into the topic that we came here for today, which is about how we apply LLMs now in our automated warehouse. Who of you is actually familiar with our automated warehouse or has heard of it? Maybe it's nice to see a small raise of hands, because then I know if I should go in depth or not. Okay, I see quite some hands, but relatively not that many. So I'll briefly explain. So in Utrecht, we have actually one of the most advanced automated warehouses of Europe, where in a normal fulfillment center, a shopper, as we call them, goes into aisles, pick the groceries to the totes of the customers. But in our automated fulfillment center, actually the shopper is standing still and the totes are moving towards the person. And the only handling they have to do is get the right amount of products from our stock and put it into the customer tote. Well, this is of course, this is important, but we also like to keep track of our inventory and of our stock, of course, how many we still have in stock, because we don't want to promise you that we can deliver the bananas tomorrow if we actually already sold out of them. And in principle, this is super easy, right? You order a set amount of bananas, you sell a set amount of bananas, and then you're left with some stock. But things happen in the process. Maybe we get a bit less bananas than we expected. Maybe some bananas went bad while handling, or they just don't look good enough that we can sell them. And that's why we actually constantly need to update our stock. And we did this manually. So on every few picks, we would ask the shopper if how many products there would be still in the tote. And that doesn't take that much time, because if you look as a person, well, 1, 2, 3, 4, 5, 6, and then you would fill it in. But if you do it on the scale of Picnic, it actually adds up to a lot of time wasted, or time that we can use for something else, if we can automate it. So that was a bit the premise. And then being pragmatic, we wanted to see what's the easiest way for us to solve this. And one of the things we immediately thought was maybe using scales, right? So to weigh the tote, maybe before and after a pick, and to see how much products there are still in there. Well, due to some various constraints, actually the scales that are installed, they have too much deviation in, well, in what they report that we absolutely cannot get on the individual product level the number of products. So then we started looking into computer vision, and it would give us actually some other benefits as well, because we can, of course, do stock counting. Well, that's the case that we wanted to solve now. But it would also allow maybe the possibility for automatically checking freshness. So has the banana maybe gone bad into the process, or damages? So maybe packaging went broken during handling. And we can also check for missing items. So when these products are picked, we can verify if the product ended up in the number of products ended up in the tote. But for now, we're focused on stock counting. So in order to use computer vision, we of course need some pictures. So let's make some pictures. Very easy, right? Those are not that great pictures. So we actually struggled quite a bit to get really good, high-quality pictures. And we had some help, luckily, also from the industry that have also done this with, at other companies. But due to some constraints that we have, for instance, that the tote actually moved very fast, that where we could place the cameras, there's actually not that much lighting. It was actually quite hard to get good quality pictures. You can tell me afterwards if you can actually count both the number of products in the right one and also tell me the product that's in there. I think I already the correct answer. Nice. Cool. But actually, we ended up with a solution that worked for us. This is actually in a setting that there was a little bit more lighting. But actually, it's a very pragmatic setup. So we have a quite relatively small camera. It has a flashlight. It has a laser. It has a barcode scanner, so we can automatically link the tote back to the. This is a GIF of it. It can automatically link the tote back to the product that we expect to be in the tote. And then we get actually super nice, high-quality pictures. So this is something we can work with. Right. Now let's make a data set, because we're going to do some eval-based development, as that is now the hype, but it's also just very logical to do, of course. So we have these pictures, and actually, like I said before, since we own our full supply chain programs and code, we actually have a lot of visibility already. So we're already counting these totes by hand at the moment. So why not just use the manual process that we have now to make our data set? So that's exactly what we did. So we got the pictures, we got the SKU that's in the picture, the number of products we think is in the picture. We got the name of the product. We also added a corrected quantity, because when we went to the data set, we saw that, yes, also us humans make actually mistakes. And we wanted to see, we want to, of course, to give the model the perfect ground truth as far as we can. And what we also actually do is for every product make a supply chain picture. So a picture of how the product would look like in our supply chain. And that's you see on the top right here. So cool, we have now a data set of thousands of pictures that are nicely labeled with a high quality confidence. We need some metrics, because we want to compare the solutions. And in our case, well, accuracy is the most important, right? We want the exact number that is in the tote to be exactly predicted by the model. If we're off, and that's just horrible. But the accuracy metric is quite a flat metric. It doesn't tell us too much if the models may be over-predicting or under-predicting on average. And what was also important for us is that if we're almost out of stock, then it's really important to be right, because that's the difference between seeing in the app if you can still order or not. So, and that's actually what we used that first secondary metric for, the MAPE, so the mean average percentage error. Basically meaning if we're off by 1, if there's 0 or 1 in the tote, or if there's 5 or 6 in the tote, then being off by 1 with 0 or 1 is actually penalized much harsher. Then we use our MSE to check for being off. So if we're off by 1, maybe in some cases that is okay-ish. Being off by 3 is more than 3 times more expensive. So yeah, that's what we use the RMSME for. And the MSD, so the mean sign deviation, we use to get a gauge of if we in general are over-predicting or under-predicting. Of course, if we're over-predicting, then more customers will see that we still have stock and will be disappointed, and vice versa if we're under-predicting. Then the data split. And this was already quite an interesting choice because, well, no-brainer normally, 80-20 data split, quite standard. But actually, when you're using LLMs, that data split might be a little bit different. And we already had LLMs in our back of our mind when we were creating this data set. And we saw, for instance, a bit of research, but also the DSPy package that is used for automatically tune your prompts. And they mention, for instance, that for prompt optimization, we suggest starting actually with a 20% split for training and an 80% split of validation, which is quite indeed the opposite what you normally would do for deep neural networks. Cool. So we have some metrics now. We have a nice data set. Which model will we pick? Well, I classified it here a bit into the more traditional way to do computer vision, which is like the YOLOs, the Tectrons, the Sven transformers, etc. Where if you have a lot of good labeled data, your performance is probably going to be good, if not really good. But their out-of-the-box performance, so the OOB, is probably not that great, right? We tried a couple of models, right, just Python packages, tried it on our data set. Even the ones that, well, if you would look at the paper, you would think, well, counting a few apples in a toad would definitely be possible, was actually very hard for these models. Well, latency-wise, we're going to reroute toads if we think that they're empty. So it's very important for us that we don't have a latency of a couple of minutes. But at the same time, our latency doesn't have to be within a second. So, yeah, in the case of traditional computer vision models, the latency is great, right? You can do multiple predictions per second, and you can quite easily self-host them. And then if we look at the, let's say, multimodal LLMs, we expect their performance when we started to be actually quite good, because we all saw these nice tech demos from the big companies doing quite cognitively hard exercises. So we expect to be quite good, and also to be out of the box already quite good. Again, with those tech demos, but also knowing that LLMs are generalized quite well. But at the same time, the latency wouldn't be that great. At the time, yeah, we didn't know how problematic it would be. At the same time, if you use ChatGPT a bit, and you get already a feeling that it's not probably going to need minutes to solve this. And self-hosting, well, for the proprietary models, it's not possible. And for the big open source models, you need serious compute, which is also not that straightforward compared to the other approach. But at least it looks promising to us. That's why we went to that approach. But then you immediately get the next question, which LLMs should you pick, right? There are lots of LLMs able to do this, especially if you just gouge by the papers. There are lots of benchmarks that are published. Some benchmarks are very close to what we're doing actually here, but then sometimes they're not updated. And since every week new models come out, there's a lot of trade-off in the costs as well. Finding a good benchmark was important for us as well, because otherwise we would have to keep up with the progress in the field as a full-time job as well. So we wanted a benchmark that required multimodal understanding, that was sufficiently hard, and that is updated regularly. And luckily, we found the following benchmark, which is named a massive multidiscipline multimodal understanding and reasoning benchmark for expert artificial general intelligence, which in itself is already quite an accomplishment if the model can pronounce it, of course. And it focuses on advanced perception and reasoning. It has heterogeneous image types, so it needs to interpret charts, diagrams, and maps. So it's quite cognitively hard to combine all that logic together, of course, with the text. And importantly, it also has some sort of human baseline. Because when we saw these pictures ourselves, and we saw sometimes the model making mistakes, we would be like, well, a human definitely could have seen that this was the correct count, right? So we want to have a gauge at how good are the models compared with an average human. As humans are also not perfect. Think of also cognitive load and having an attention span. But we found this one. And it's not about all these individual models, but they made this very nice graph where you basically see two trend lines, the red one and the blue one. The red one being the proprietary models and the blue ones being the open source models. well, first of all, very important to see that they're, they're how do you say, conquering these benchmarks quite rapidly, that the slope of them is quite similarly, and that is only 9 months or approximately difference between having the best proprietary model being beaten by the best open source model, which then allows us to have extra flexibility in the future. So cool, from this we of course could pick a nice model that would both perform quite well, but also be within reasonable cost, because indeed if we just go up the slope and get the most important GTP5 with thinking mode on every image just to count a few stock, then probably that business case won't work. So we have a model from this. So we can count. Sometimes we can still not count. Yes. So yeah, we were quite happy with ourselves, and then indeed we saw quite some pictures being taken of products that are completely blocked by carton, that are completely stacked on top of each other, that sometimes you have the inner product with some sort of carton around it and then they get loose, and it's, as a human you can clearly interpret this, but as a model this is quite hard. And this is then what we classified as the countability check, where we first want to check, is this even an image that even a human can count or not? And if a human can count it, we expect the model to be able to count as well eventually. But if a human cannot count it because indeed things are blocked, we're not going to try in those cases. We still have to have the physical human there that can actually unstack things, get the carton out, and do it themselves. Luckily, this was not this was a large part of the data, but not like still okay is that we could continue. But we did want to focus on our accountability check, because if this would fail, we would basically send a lot of wrong predictions. So to make accountability check, we again go to this loop. We want to have some sort of metric to check how well we are doing. So we use precision and recall in this case, where for the precision of all the images the model said were countable, how many were actually countable, and for the recall was of all the images that were truly countable, how many did the model successfully identify. And while we were already using LLMs, and we were quite comfortable having them predict the number of products in the tote, we thought, well, let's also apply it here. It was actually horrible. And then we tried a couple more prompts because we got a bit better, and we tried prompt optimization, and it was still horrible. So we went back to the drawing board, and we actually collected all the images that were being predicted wrongly by the model, and just embedded those, and to see if we can get a few clusters. Because, like I said, we had thousands of images, and going by hand through it as a human, we kind of couldn't really get to some sort of distillation of it. But based on this, we actually found these nice groups that, for instance, said that there were carton because the carton was blocking, or they were stacking, and that all happened with always the same type of products and the same type of packaging. So we made a few rules, and actually it outperformed the models way better, which was again, of course, a good reminder for ourselves that having a good rule is just super nice. Cool. So now we have the model, we have accountability check in front of it, we have some prompt and the image, and actually this was still not working that well. The model was often being distracted by having stickers in the tote and by having some reflections in the tote. Sometimes the products would be upside down, and the model would simply count it. And we spent a bit of time on prompting, but also knowing that prompting is basically giving context to a model, we thought, well, we have a lot more high-quality context that we can actually give the model, also in images, which in our case is that supply chain image. And the moment we added that one, it all of a sudden shot up in accuracy, and also in all the other metrics went down in the right approach, right direction. And we were getting very excited that this would solve it. But then we would solve it maybe with the best model, but did we also solve the business case, right? Could we do this with a model that would be cost effective? Well, for that at the time, Gemini was the best performing, also cost effectively on that MMU benchmark. So we tried with Gemini 2.0 Flash, which is their cheapest model. And I've normalized here the values a little bit, but that doesn't mind. Yes, and we actually, so Gemini 2.0 Flash, which is here 100, we were not super happy with the final result. But it would be cost effective. Well, then we went to 2.5 Flash, which would be cost effective, but actually it was still not on a level that we had hoped would solve our business case. So then we flipped it around and said, okay, what if we give it to the best model out there, at the time 2.5 Pro, to see would it then solve this problem even? And for us, that 114 here would definitely solve the problem. So we were very happy, but now we had to bridge this gap, right? How do we get from 2.5 Flash to 2.5 Pro with the cost benefit of 2.5 Flash? And that's, well, we already had a very high quality data set and basically applied some fine tuning. And all of a sudden, our 2.5 Flash was outperforming the base 2.5 Pro. Obviously, if you start fine-tuning that model, it probably will outpace it. But for us, to make the business case, this would be the most pragmatic approach. So that's what we went for. Cool, we have the model. It's all nicely working. We're going to bring it to production. But how do we know that in production it will continue to work well? I'm not sure if you saw a recent paper of Anthropic, where they said that over the summer, they had a degraded performance, and it was not because they made some changes to the model, but it was purely on the infrastructure level. And of course, if that would happen to us, or if it would happen at this cloud provider, then it would be detrimental and very impactful for our operations. So we, at a constant time, we would like to keep an update of how well is the model performing. Well, luckily, we already have the existing flow. What if we, for almost 100%, do it automatic, but then for a very small percentage, we would also still ask the shopper to recount it as well. So that's actually the approach that we went for. And now we need to productionize it. So we bought 16 camera setups that are all spread now to FCA. We created a fast API web service that when it gets an image, it immediately actually sends a request back with a background task. It actually returns the request immediately to the camera so that the camera is unblocked. And then collects all that extra information that I was talking about. So it collects the prompt, it collects the supply chain image, and forwards that through light LLM, so LLM proxy, to, in our case, Gemini. And we put a light LLM in front of it, because like we already saw during the development, we were switching quite often between models, right? As you know, every week new models come out. They get either better, or maybe in the case of Grok, this week it got 47 times cheaper for almost the same performance. And we immediately want to use these benefits, of course. So we planned for this interchangeability from the start by already having a light LLM proxy in front of it. Then we make our predictions. We send that to our control software, but we also publish that to Snowflake. And in those small cases where we ask for a validation count, we WCS actually puts also that information as an event to Snowflake. So let's recap a little bit. Our learnings from this was that we boost LLM performance on our domain-specific task by leveraging the unique context that you have. So in our case, that was that supply chain image. Adding, for instance, using, for instance, DSPy that optimizes your prompt didn't really work for us. And I think, and maybe one final thing to note there, when you, for instance, have a customer agent robot and you prompt optimize it, then adding the role or adding the tone of voice or adding examples in those cases of your specific company probably will work. But in our case, it doesn't really matter if you see groceries or if you see screwdrivers. It's counting the number of products that are in the tote. So for us, prompt optimizing didn't really work, but adding that unique context that we can give it really boosted the performance. Then fine-tuning those mini models can outperform the pro models. So you definitely don't always need the pro models. Proprietary LLMs have gotten really good in the past year on visual tasks. Open source models are roughly 9 months behind. And the first big open source models that are actually usable for this are now coming out. We planned for LLM interchangeability from the start, and we're already reaping the benefits from it. And finally, and this is often often said in the data science talk, but I'll say it once more, that analyzing the mistakes and adding a few simple rules can actually fix most of those mistakes. Cool. If this sounds very cool to you, we are hiring more ML engineers, also on this topic, but also on the various other topics that I briefly discussed. I've added here our career page for that. And also, if you want to talk about this or anything else, you can add me on LinkedIn. Thanks a lot for your time.